Hello everyone! In this video we will continue to examine topic 5.1 electric fields, and in particular we will introduce the idea of electric fields. So up to this point we have examined Coulomb's law, and we know that charges affect each other at a distance. But the question will be, how is that possible? To back up a little bit, Coulomb's law is a law that tells us, okay, we have this charge over here, and then we have this charge over here, and they're so far away. How big is the force that one of them applies to the other? Coulomb's law is a descriptive law in that way. It sort of describes what is happening. It tells us what the force will be. But it doesn't explain how. And in fact, in our initial sort of writing down or description of Coulomb's law, there is sort of a fundamental mystery that bothered scientists at the time, which is this force seems to sort of be applied instantaneously at a distance. This is known in modern terminology as non-local. So this force, as written with only Coulomb's law, is non-local. It's happening because of this thing over here immediately, with no time gap. And that's kind of strange. And so we're looking for an explanation of how that could be. Moreover, there's actually another sort of use for the answer to this particular question, which is how can we figure out what force a complicated charge distribution, something ugly, imagine you had a random piece of metal with a whole bunch of positive charge on it, how would we figure out what that random piece of metal would do to a charge near it? Okay, what would that force be? Because remember that Coulomb's law only applies to point charges. And the answer, as you might have guessed, is this concept, this idea of the electric field. The electric field both answers this question, how the electric force is applied, and is useful because it allows us to answer these kinds of questions more easily. And we'll see both in turn, okay? Both of these uses in turn. But the big point is conceptual. So what is electric field? Well, here's the summary answer. The thing to sort of codify in your mind is what the electric field is. Charges affect the space around them, not just each other. This charge is going to do something to the space around it, and it's going to change what's called the electric field in that area. This electric field is real. And in fact, in modern physical theories, we think fields are some of the most fundamental things there are. The field itself is invisible, okay? But it can be described and it has very predictable properties, okay? It will do different things. So one of the things that it does, and the sort of the essential ingredient here, is that the field in that space then itself produces the electric force on the charge. So in some ways, we're going to make this explanation more complicated. It's not that this charge applies a force on this other charge, although you could describe that as being what happens. It's that this force, how does it do that? It creates a field around it, and that field in this area of the other charge produces the force. And this fixes the affecting each other at a distance problem because it's not instantaneous. The charge first produces the field, and that takes some time. In fact, that influence propagates outward at the speed of light, and then that field produces the force. Okay, and so that's the idea of electric field that we're going to move forward with. So let's unpack that a little bit. Okay, let's unpack that a little bit. And again, the most important thing in these couple of sections is just this idea of the electric field. What is it? What is it doing? What is the concept for? We will get into calculation first, but it's very important to get these ideas down before you start calculating, because the calculating can sometimes, I think, obscure what is actually going on. So in this case, right, this is the same sentence as before, but there's a different diagram here, designed to sort of partially help show what's going on. So these positive charges are in some distribution over here. They're fixed. This thing is positively charged. And then the field that is produced by these positive charges permeates outwards. Okay, and these arrowed lines will eventually be called field lines. Okay, and there's sort of a grid imposed on that, although it's important to note that that grid is not a correct or full representation of the field. It's just designed to show that the field is everywhere in this space around that charged object. And then that field, okay, visualized by those red lines, although it's not actually visible, interacts with this other positive charge over here to produce the force, that electric force Fe shown right there. And that's a force not on the original charges, but on this new charge. So the idea is that these charges produce the field in red, and then that red field interacts with the positive purple charge to produce the force. Okay? Note that the positive purple charge shown also produce its own field not shown here, just for simplicity's sake, so that we can get the idea. Okay? Now, we're going to formally define this and figure out how to calculate it. And that formal definition, in some ways, will be useful, will be important, and you will need to memorize it. But this is the essential idea of what's going on, so let's never lose sight of that. Okay? So we're going to define the electric field. The IB calls it electric field strength. But as a side note, I simply can't abide by that terminology because electric field strength is the kind of phrase that really should be used to describe the strength of the electric field. And the electric field itself is a vector. The IB says the electric field strength is a vector, which is a weird thing to say. So the electric field is a vector, and the formal definition is that it is the electric force per unit charge, that's important, that would be felt by a small positive test charge placed at that point. We're going to unpack this. This is a weird definition, okay? But we'll unpack it. It's the electric force per unit charge that would be felt by a small positive test charge placed at that point. Okay? The idea is to figure out what the field is going to be right here, for example. We use a conceptual tool. We mentally place a positive charge there, a small one, so that it doesn't disrupt the field that it's measuring, so to speak. And we ask ourselves, all right, how much force per amount of charge that you put there, because if you put more charge, it'll feel more force, per amount of charge, would it feel if you placed it there at a particular point? Okay? That's the idea behind this formal definition, and it comes with an equation. The electric field is defined to be the force, electric force per unit charge. For those of you who have seen limits in calculus, strictly speaking, a more accurate version of this definition is that the electric field is actually the limit as Q goes to 0 of the electric force divided by the charge. So when we say small positive test charge, that's the IB's way of sort of gesturing towards this idea that we don't want our small positive test charge to influence the field that we're supposedly measuring or defining. In other words, like the field of this guy is independent of and shouldn't be accounted for when considering the force that charge eventually feels, because the force that charge eventually feels is only due to the other charges, not due to its own charge. Charges can't affect themselves, is another way of saying that. So this is our definition, and it's the force per unit charge, the electric force per unit charge that would be felt by a small positive test charge placed at the point. Now, why positive? Well, the truthful answer is that's simply by convention. So you could have electric field that was the force per unit charge felt by a small negative test charge placed at that point. That would be a completely consistent definition. But we use positive by convention for the same reason that in a given country, everyone is going to want to drive on the same side of the road, even if that side of the road is different from different countries. So this is a conventional thing. Okay, the unit is newtons per coulomb. We'll discover there are more units for this, but for now, we'll start with newtons per coulomb, as you can see, newtons per coulomb. And it is a vector quantity. Okay, so electric field has a direction. If the force per unit charge would be to the left, then the field is to the left. If the force per unit charge on a positive test charge would be to the right, then it would be to the right. And the positive or negative would switch the directions if you change that definition. More accurately, I should be a little bit careful, the electric field is not itself a vector. It's strictly speaking a vector field, which is a formal kind of mathematical object. And the idea is that the electric field is not just a thing with a direction, like a force. Okay? There is a magnitude and a direction of the electric field at literally every point in space. So we can ask for what the electric field is right here. Okay? It would be big and away, because the force on a small positive test charge right there would be large and away. Whereas it would be smaller out here, because the force on a small positive test charge would be smaller out there. So there is a field direction and size for literally every point in space. That is what vector field means. For the IB, we're comfortable simply calling it a vector. We'll get to the electric field of a point charge in the next video.